Good morning, everyone. Today, we embark on a fascinating journey to explore one of America's most iconic landmarks, a true marvel of human ingenuity, the Golden Gate Bridge. This isn't just a bridge, it's a testament to engineering the impossible. Connecting the vibrant city of San Francisco to Marin County, it's a vital link, gracefully carrying approximately 40 million vehicles each year since its completion in 1937. We'll delve into its remarkable design, its robust structure, and its incredible resilience. Imagine the audacious challenge faced by its creators. The project demanded conquering a strait notorious for its violent winds, sometimes reaching up to 60 miles per hour, along with strong ocean currents and a deep water canyon. Adding to the complexity, it sits less than 8 miles from the San Andreas Fault. Yet, between 1933 and 1937, with an initial budget of $35 million, a team of visionaries brought this dream to life. Chief Engineer Joseph B. Strauss, the original concept architect, bravely proposed a hybrid design. Leon S. Moiseiff provided the theoretical breakthroughs for its unprecedented long-span suspension. And Irving F. Morrow, the consulting architect, gave us its timeless Art Deco styling and that unforgettable international orange color. Ultimately, the project came in slightly over budget at $36.7 million, a small price for such an enduring masterpiece. Let's uncover the secrets of its magnificent suspension system. The main cables, each an astonishing 2,332 meters long and nearly a meter in diameter, are too heavy to simply lift into place. The solution? An ingenious process known as spinning in place, using Roebling's parallel wire construction method. Can you believe each main cable is comprised of 27,572 individual strands of wire? This meticulous, wire-by-wire process created a structure so strong, yet so flexible, that its parabolic sag allows it to bend an incredible 27 feet laterally in strong winds, a true testament to its brilliant design. The majestic towers, standing 227 meters above the water, presented their own unique challenges. The North Pier was constructed on a bedrock ledge, a relatively conventional approach for its time. However, the South Pier was an entirely different story. It had to be built directly in the open ocean. Engineers achieved this feat by constructing a massive watertight cofferdam, essentially a temporary dam, to allow them to pour an incredible 147,600 tons of concrete for its foundation. Both towers utilize cellular steel construction, designed with flexibility in mind to allow for lateral movement, crucial for enduring the forces of nature. Now, let's explore the incredible dance of forces that keeps this magnificent bridge standing. It's a symphony of engineering. The load from traffic and the deck's weight is first transferred to the suspender ropes, which are in tension. These ropes then pull upwards on the main cables, also creating tension. Finally, these main cables compress the mighty towers vertically, while pulling on the anchorages, relying on friction and normal force. It's a brilliant system where every part works in harmony to resolve and distribute immense forces. One of the bridge's most distinctive features is its iconic color, international orange. But why orange? It wasn't just a random choice. Its practicality is remarkable. The high contrast of this warm color against the frequently dense fog significantly enhances visibility for passing ships, ensuring safety. Aesthetically, it's a stroke of genius, a warm earth tone that complements the surrounding landmasses and beautifully contrasts with the cool blues of the sky and sea. The credit goes to consulting architect Irving Morrow, who, during construction, admired the red lead primer color so much that he chose it over the originally planned black or gray. As Mr. Morrow himself elegantly put it, the effect of international orange is as highly pleasing as it is unusual in the realm of engineering. Every aspect of the Golden Gate Bridge exemplifies the principle that form follows function, creating both beauty and utility. Take the diminishing portal size on the towers. The rectangles subtly get smaller as they ascend, forcing a perspective that emphasizes the bridge's incredible height, making it appear even grander. The vertical ribbing on the towers is not just decorative, it captures sunlight to create captivating textures and shadows throughout the day. Even the lighting strategy is masterful. At night, the towers fade into darkness at the very top, giving the illusion of reaching endlessly into the sky. Its overall Art Deco style, along with modest, uniform railings, ensures unobstructed, breathtaking views for everyone who crosses. The bridge's design also courageously confronts the threat of aerodynamic instability, or flutter, caused by powerful winds. The primary defense against this challenge comes from the stiffening trusses, an impressive 4,700 tons of steel lattice integrated into the bridge's deck. These trusses are ingeniously designed to break up wind flow and resist any twisting or torsional movement. Originally, the critical flutter speed was 60 miles per hour, but through continuous improvements, it's now rated for winds exceeding 65 miles per hour. A dramatic example of its resilience occurred during a storm in 1951, when 70-mile-per-hour gusts caused a lateral sway of nearly 14 feet, yet the bridge stood firm, a testament to its robust design. Living in California means living with seismic activity, and the Golden Gate Bridge is no exception, located between the Hayward and San Andreas faults. From its very inception, it was designed to withstand an 8.3 magnitude earthquake. And it passed a significant real-world test in 1989 with the 7.1 magnitude Loma Prieta earthquake, emerging with no structural damage. The structural strategy is brilliant. It prioritizes flexibility over rigidity. The philosophy is that the entire structure moves with the energy of an earthquake, rather than resisting it stiffly. The anchorages move with the ground, while the suspended span is cleverly isolated from the towers. Of course, engineers continue to identify and address vulnerabilities, such as the approach towers, cable connections, and the Fort Point Arch, to ensure its enduring safety for generations to come. To further enhance its seismic resilience, the bridge has undergone extensive retrofitting in phases. Phases 1 and 2 focused on the approaches. For the north approach, this involved strengthening the foundations and replacing support towers with mechanical isolation and reinforcement. The south approach and arch presented unique challenges. Here, engineers implemented sophisticated energy-dissipating devices, essentially friction dampers, to control movement between the arch and the pylons. Additionally, seismic isolation bearings were installed at the roadway level, and internal shear walls were added to the south anchorage, all designed to absorb and manage earthquake forces. Phase 3 of the retrofit concentrated on the main span, incorporating even more advanced technologies. Strategic implementations include fluid-based viscous dampers, acting like giant shock absorbers, to cushion the impact during high displacement from seismic events. The cellular steel construction of the towers was further reinforced. Pre-stressing with steel tendons was added to the pier bases for enhanced stability, and internal stiffeners were introduced to the tower cells to prevent buckling. These measures ensure that even the core of the bridge is prepared for future challenges, embodying a commitment to unparalleled safety and longevity. A significant modernization project was the orthotropic deck upgrade, completed between 1982 and 1986. The original deck, made of heavy reinforced concrete, was replaced with a much lighter, yet incredibly strong, orthotropic steel deck. This was a truly visionary change. The benefits are numerous. A dramatic weight reduction significantly lessens stress on the main cables, extending their lifespan. It also greatly increases the bridge's torsional resistance against powerful winds, enhancing stability. Crucially, the new deck is structurally integrated with ribs and floor beams, becoming an active part of the bridge's load-bearing system. This upgrade truly showcases how this historic marvel continues to evolve with cutting-edge engineering. Maintaining a structure of this magnitude, exposed to the elements, is a continuous labor of love and dedication. Corrosion is a constant battle against the relentless salt spray and fog from the Pacific. Dedicated on-site crews work year-round on a continuous maintenance painting cycle, ensuring the bridge retains its vibrant international orange. Safety is paramount. The recent installation of a suicide deterrent netting, a monumental engineering and cost hurdle, underscores the commitment to saving lives. Additionally, a movable median barrier provides enhanced traffic safety, adapting to daily flow. This vital link continues to serve as a critical artery, accommodating approximately 40 million vehicles each year, a testament to its enduring utility. To truly appreciate the scale of this masterpiece, let's look at some astounding technical data. The total length of the Golden Gate Bridge spans an incredible 2,737 meters. Its majestic main span stretches 1,280 meters between the towers, which themselves rise 227 meters above the water. A clearance of 67 meters above high water ensures ample passage for ships. The original structure weighed approximately 811.5 million kilograms. The towers alone comprise 40.28 million kilograms of structural steel, with each main cable containing an astonishing 27,572 individual wires. Interestingly, much of the steel was sourced from Pennsylvania and New Jersey, making an epic journey through the Panama Canal to reach its final destination here in California. In summary, the Golden Gate Bridge stands as an enduring icon, a perfect synthesis of form and function. Its graceful Art Deco style expertly reduces visual mass, making it appear lighter than its colossal size. The international orange color, far from being arbitrary, ensures both visibility and aesthetic harmony. And its pioneering suspension design truly conquered the impossible, proving that human vision and engineering prowess can overcome the most formidable natural challenges. Its legacy is immense, serving as a global benchmark for engineering aesthetics and a living case study in the successful retrofitting of historic infrastructure. As Irving Morrow so beautifully observed, the bridge color was a very important influence on its appearance. A colorful symphony of the hills. It remains a timeless marvel, inspiring all who gaze upon its magnificent presence.